Lecture 16 is going to be on parallel database systems. Lecture 17 is going to be on distributed. There are two more lectures having to do with LSM trees, log structured word trees, and spatial database that we may or may not get to. We'll probably get to be able to discuss at least a little bit of either or both on the last day of classes. But since both the parallel and the distributed database material are on the final, I'm going through those first. And we'll be spending today and possibly part of Monday on this, and then between Monday and Wednesday we'll be finishing up on lecture 17, which will involve distributed database. Reminder about some notices, about project 4, which is due on a week from yesterday, the last project of the quarter, and you know how all that rigmarole works. And there's a final in this room on Wednesday, June 12th from 4 to 7 p.m. covering the entire term. No Scantron sheet, no booklets necessary, just you can bring a cheat sheet, 8.5 and 11, with anything that you want written on it. I posted last year's final, but there aren't answers to that, and I'm sure as we get closer to the end of the term, there will be some questions that get posted having to do with the answers of that final. Could be that we'll spend a little time on the last day of the class if there are certain questions that a lot of people have trouble with discussing one or two of those questions. And of course, there are these evaluation things that are out there that opened on Sunday and closed the day before finals begin. Reminder that it's great to fill those out because it can help improve things in the future. Instructors can't see the answers. In fact, we don't even see the aggregate answers until a month after that, so it's after grades are in. So please fill those out and express your opinions constructively. That's always useful. So let's talk about parallelism. And I mean, as you're going to be seeing, parallelism in database has been a great success story from very, very early days. One of the first early success stories, because I will remind you, going back to 180, the great thing about queries written in SQL is that they are set oriented. They are functional, which means that they don't have any side effects, right? So the order in which things operate is great. They are declarative, meaning you don't have a particular way of doing things. You're just trying to take something which is a fairly high-level language and finding a way to be able to do it. And parallelism can be a great advantage. So databases ended up being able to get great stuff in parallelism from very, very early days, as we'll see. So, I mean, basically, you've got a straw. And let's suppose, original version of this slide, by the way, said 10 megabyte. Here it's 10 gigabyte, but even that is small these days. But basically, if you have a straw and you're sucking data, okay? You may feel that data sucks, but here you're using the straw to be able to get at the data. I don't know how you feel after this class. I guess I'll find out from the evaluations. But if you end up having something which is a petabyte, right? And petabytes aren't that big these days, right? I mentioned in 180, Jim Gray, who I keep mentioning in the class, gave a talk about 10 years ago, which was called a terabyte, spelled T-E-R-R-O-R, because at that time, thinking about managing a terabyte, which is 1,000 gigabytes, sounded like it was scary. These days, a petabyte is relatively routine for a lot of things that people do, not typically for databases, but other data management systems. And so if you have a petabyte, which again is 1,000 terabytes, so a million gigabytes, if you have a straw and all you can do with going through the data is 10 gigabytes per second, it's going to take 1.2 days to be able to scan it. On the other hand, if what you can do is have 1,000 straws, that's not quite 1,000 straws here, but use your imagination. If you can go ahead and have 1,000 straws instead of one to be able to go through the data, and you're going through all of it, well, it's going to divide the amount of time by 1,000. So that's going to be about 1.5 minutes to be able to scan through that petabyte of data. The whole idea of parallelism is find a way of dividing a problem into smaller problems that you can solve and deal with them in parallel. And that's the subject of this lecture, trying to use parallelism. Of course, if the individual problems are independent, this is termed embarrassingly parallel. Some problems are very, very easy to work with separately, and database actually takes advantage of that for a lot of things that we do. Sometimes parts of problems depend on other parts, so they're not embarrassingly parallel, and it's hard to be able to split things up. So here we're going to talk about how things are natural to database. And one way that things end up being, very parallel is pipeline parallelism, and the other is called partitioned, or sometimes sharded parallelism. But why is pipeline parallelism, useful? Well, you've got a series of steps in a plan or in a workflow, where you need to do A and then B and then C and then D. And if you're producing the results as you go, you produce the results of A, and you produce the results of B, and you produce the results of C. If you don't have to wait until the entire answer is available to you, as things come out of A, you can start working on them on B, and as things come out of B, you can work on them on C, and all the way along the way. So that's one way you can do it, just have each step in the pipeline capable of working on things as they pull them or get pushed to them, depending on how you're working. And then there's the sharding and distributing of things. I'll mention right now, the word partition has traditionally been used for this, and it's still used mostly in database to talk about splitting up the problem into 1,000 straws. You have 1,000 pieces. You break up the data into 1,000 pieces. Each piece works on its own part of it, and as long as there aren't correlations between the different parts of it, you can work on these things in parallel. There are lots of different things that are hard to split up that way. For example, if you're trying to look up things like paths in a graph, there are ways of dealing with that with parallelism. It ends up being harder to be able to deal with. If you're dealing with matrix multiplication, there are ways of dealing with that in parallel, but it's a harder thing to split. Let me just go through the point of partitioning, and then I'll take the question. So the term partition has typically been used, it's still being used. People get confused between splitting data into various pieces, which are now often called shards, and the notion of a network partition. A network partition is when you have one part of the network that can't talk to another part of the network. And so that term, the term partition is overloaded. Heck, everything in computer science, the term is overloaded. Object is overloaded. Thingy is practically overloaded. Everything is overloaded. But often you will find the word shard instead of partition used in this case to avoid the problem. But if you can split one step into 1,000 pieces that you can do in parallel, and the next step you can split into 2,000 pieces that you can do in parallel, then again, that's a way of being able to get better performance out of the things, as long as the pieces don't have any dependency on each other. The next step may have a dependency on earlier steps, but no step, if you have a situation, and this depends on your computation and how you design an algorithm for the computation, where none of the steps that are shown here with all these different bubbles, which is like 1,000 straws, if you can split it up, then you end up getting a big win on operating in parallel, and maybe by throwing additional resources like extra cores and memories and so on at the problem, you can get things done in 1/1000th of the time, or whatever the factor is. Now the question.
You may have answered this with your overloading comment, but does this have any correlation to the partition by syntax from SQL?
Heck yes.
Okay.
That exactly is the point, and we're going to see examples of this in this lecture. And time for usual bad joke. The First Amendment guarantees the right to partition. Anyway, still have a few more left, folks. 4 lectures, counting this one until the end of the term. Okay, so for a long time, databases were the really successful use of parallelism. Not necessarily the only, but really important, because it was so natural to take SQL queries and find ways of working on the different pieces of the query in parallel. Whether it was different operations in a single query, right? Or it was things where you could go ahead and operate in parallel on different partitions in the query, different shards, or also getting parallelism by having different queries being run separately. There are lots of different ways of getting parallelism. We'll come to a bunch more of them when I come to a slide about some of the stuff that SAP HANA did, but lots of other systems besides SAP HANA do it. That's sort of the end of this lecture. So there are lots of things out of Teradata, out of a company called Tandem, which is the place that I worked after IBM Research, working on the transaction manager, thinking machines, Kendall Square Research. Everybody, basically at this point, everybody has lots and lots of parallelism. If they didn't, they would lose. It's a great way of being able to handle better response time, better throughput, scalability. It just ends up being a huge win. It does take resources to do the parallelism. And by the way, one of the scheduling things, and an aspect of database that we don't talk about in this class is scheduling. How much parallelism do you throw at an individual problem? Who gets to go first, not because of deadlocks, but because of a deadline for getting answers to queries? Really, really tough, interesting sorts of questions. But the world isn't data. The world today on data, there was a time when I would say, well, database has less than half of the world's data in it because things were kept in files. At this point, you have all the different things that you're doing with big data, okay? And you've got this variety and velocity and veracity and all sorts of V's that get thrown on big data, including volume. You have all sorts of things that aren't stored in database. You don't need the transaction processing capabilities, but you do need to be able to do querying of that data. So it has elements of database, but not the full elements, or even are usually SQL interfaces to most big data. So there is a huge amount of data that is not stored in databases. Some of it is in file systems and just manipulated using file primitives, but a lot of it is manipulated using big data capabilities such as variations of MapReduce and Spark and Hadoop, which are all cousins of each other. And all sorts of other big data paradigms, again, which have a certain amount of relationship to database, even though the data is not stored inside database. So again, set-oriented means that it's easy to go ahead and work on the different pieces. It's not something where, oh, I've seen this value in my 5th tuple, well, I have to do something different in my 6th tuple and 7th tuple. They're independent. It's set-oriented and it's functional. There's natural pipelining of the relational operators. We've seen pipelining and doing relational database multiple operators. You can throw a lot of relatively cheap hardware. You don't need to have that much special purpose hardware. Although, believe it or not, for certain operations, lots of things like GPUs and FPGAs and special hardware are making a comeback to be able to do certain specialized operations. And the point is that you write the query. You don't have to say, oh, I want to split this up into 1,000 pieces or 5 pieces or whatever, just as you don't have to understand what the detail of the plan is. You've got a contract with the database to execute your queries and updates and so on. What plan it uses, including how much parallelism it uses, is the business of the database. And today you might get 3 cores and whatever number of memory bytes, and tomorrow you might get 1,000, and everything just runs. Everything just runs. In fact, parallelism as part of the plan is a very interesting thing to deal with that we haven't discussed a whole lot when we talked about optimization, but it is part of it, both figuring out about general optimization and figuring out about execution in a particular environment. For example, if you create a great plan, assuming you're going to get 100 cores and you only get 3, what do you do about it? Maybe the 100-core plan wasn't that great. Okay, and terminology, the speed up versus scale up. Sometimes called scale up, scale out. What does speed up mean? Okay, basically what you're trying to do is to see what you can do about making things run faster by throwing more hardware at a problem for a given amount of data. So you throw more hardware to be able to for a fixed amount of data to be able to speed up the way things executed. But there also is an issue about scale. So the top one is about running a query faster. The bottom is running more queries, right? It's being able to have elasticity. It's being able to expand and get, great throughput where 99% of your queries finish in under 300, milliseconds. Even as you have more and more queries coming in and being able to work with that, you'd like to be able to make that work. I mean, not necessarily everything, but almost everything coming back in a given amount of time. And these days, maybe close to everything. Now, also terminology. Many of you have, well, how many of you have heard the term SMP, or shared everything? Some of you have, a lot of you haven't, interesting. Well, basically, you can have a really big computer where basically, although it can have a lot of different threads going on, logically, it's got one copy of the operating system. Logically. There can be a lot of different things going on, but logically, there's one copy of the operating system. Logically, there is one cache that is being shared. And making SMPs work with more and more processors, this is something that a lot of companies like Sequent and SGI and Sun was another company that I worked at, tried to do really well with this, particularly for database applications, but also for others. And so the idea is, again, that you've got, all these different processors, and logically there's one copy of the operating system, which means it's easy to program. Assuming that I have something that works on an SMP with, 4 processors, I don't have to change that program for it to work on an SMP with 8 processors. There's a free launch. To the extent that you can do scale up on that SMP, and scaling up more and more processors ends up being really complicated to be able to do, because you have to deal with cache coherency and all sorts of things there. You have to basically make it look like there's a single cache, and change that happens in one place should be something where it won't be a problem for something working in another place that's using those values. That's shared everything. Logically, there's one computer, and there's a whole lot of mechanics underneath to make that happen. Then there's shared nothing. Shared nothing has the opposite values. Making it work is relatively easy. Making it work efficiently is kind of interesting, but making it work at all is relatively easy, because what you're doing is you're splitting things up across 1,000 different processors. It affects your programming model. You're programming to be able to work on top of n processors, or whatever the value of n is. Maybe a fixed n, maybe whatever n you can get. And you're being able to work with that. And it's easy to build, and it's easy to scale. I mean, if I want to have, 100,000 instead of 10,000 processors, well, I need 100,000 processors, but working on a cloud environment, I just have to ask what resources I have and deal with allocations. Yes, I do have to deal with delays and failures and all the rest of that in that environment. But it's relatively cheap and simple to build and to grow to more and more and more, as long as you can program to that model. That's a shared nothing model. And in between, there's a notion of shared buffers and shared disks. There's a notion that everybody can get all the disks, everybody can get at all the disks. Instead of in the shared nothing, you might be assuming that everybody has different storage that is associated with them. And so it's something, it's sort of in the middle. It's what, variations, VMS cluster, VEX cluster did, IBM Sysflux does. It still relates to some extent with by the way Oracle is implemented. Oracle operates with a kind of shared disk environment with their architecture, which is kind of different from everybody else's. But again, advantages, left-hand side, very easy to program to. Hard to build. Right-hand side, very easy to build. Harder to program to. You got to split the thing up into different pieces and deal with what cross interactions might be, or try to eliminate them or reduce them, or deal with different stages and steps when that occurs. And the middle one ends up being something where it ends up being specialized. Again, hard to be able to build and be able to scale, although Oracle has done a nice job of it over the years. So we've talked about different types of parallelism that you can have in database or other data management. Basically, what you can do is take an operator, and we're going to talk about examples of this, and find a way to implement that operator like a join operation, and have it work with a whole bunch of different things going on in parallel that do that one single operation. And you can see how that works nicely on a scan. We'll talk about how you can do it for sort. We'll talk about how you can do it for join. Scanning, having 1,000 straws, pretty easy. Just have to put the results together. Okay? Inter-operator parallelism, that's that pipeline we were talking about. You do A, and then the results of A go into B, go into the results of C, et cetera, et cetera. warning, that only works when you don't need the complete result of A before you do B. We'll talk about examples where the pipelines get blocked, where you do need the full result of A before you can do B. And then there's inter-query parallelism. I'm doing totally different queries. I can throw different pieces of hardware and memory at these different things. We will be focusing on the first one, the intra-operator parallelism, and talking about that, because both of the last two are kind of easier, although I will talk about blocking a little bit, what goes on there. So here is our sharding / data partitioning as it exists. And again, mostly you'll find sharding used in a lot of academic papers. In the database systems, they use the words partition because they always have. So it's there. And here are 3 ways that you can partition a table. One way you can do it is you can partition the data by range. So you have names that are between A and E that are going to be stored with respect to, and by the way, we're focusing on shared nothing here. So you're going to have A through E, F through J, K through N, O through S, and you can end up processing. So if I'm looking up, where name equals Finkelstein, I know I can just direct it to this one place, and I can ignore the others. I don't have to go ahead and look at every partition. I can do what's called partition pruning. I can just go to the thing that has F. Or if I'm looking for names where the name is somewhere, the first letter of the name is between H and let's say P. The first letter of the name is between H and P. I know I have to look here, but I only have to look at things with an H. I have to look here, and I have to look at part of the stuff here, but I don't have to look at this piece or that piece. So, I can look, and in fact, I can look in parallel in these 3 places, but I can prune off and not look at those 2 places. So partitioning, by range of values, that has some advantages. There's another approach, which is our good friend hashing. So basically, what's going to go on is that they're going to be, I'll be using the hash function to be able to store things. So if my H value, ends up going over in my first partition, then I'll go to my first partition. Let's say a partition based on, 17 hash values, 17 being my favorite random number. Then if I'm looking for a search of Finkelstein, then I get hash of the value, and I know which place to look, and either Finkelstein is there or it isn't. So it's great for able to do that. It also will help us with certain equi-join queries, right? Just basically standard join queries. And in fact, we're going to be talking about Grace hash join in the presence of parallelism in a little while. There's another way, which is called round robin. And there is a disadvantage to particularly to the first approach, which is that you can get skew. There are lots of people whose names begin with W through Z. And you're going to have a lot of data over here and probably a lot of queries about that data and less so about the others. So things end up not being even. They're probably going to be pretty even unless you have that same value showing up, exactly the same value, but they'll probably be pretty even for hashing. But a way, if you want to ensure evenness just about perfectly, in fact perfectly, is to use round robin. What does round robin mean? When you're inserting values, you put first thing that comes in the first partition, the second thing in the second partition, the third in the third partition, fourth, fifth, etc., etc. Yeah, it can get affected by inserts and updates a little bit, but randomly the inserts and the updates probably should be fairly scattered across. So round robin ends up being something that scatters everything across. It's better spread than by far the range. Hashing tends to be pretty good on that as well. So again, the hashing is great for exact match or equi-joins. It's not good for ranges. But round robin is terrific, spreading everything around fairly. Now remember, I can do all my queries with any of these approaches, because I could just go to all the partitions. I can always go ahead and go to all the partitions to be able to find things that I want. Okay, so for sure, nothing to work, having good partitions is great. Otherwise, there's skew, and so the shared nothing. I can end up having, if everybody's W through Z, I will end up having most of my data accesses over there, and not as many over there, and I won't get. What I want is having n processors. I want to have close to 1 over n of the work, being directed to each, which is great for my scale. So if I want to be able to do scan, let's take that operator. We're going to go through a number of operators. I want to be able to do scan, and I want to be able to do, something where I'm also doing selection on the scan. No joins involved, just scan with selection and projection going on. Then what I can do is I can do the scanning in parallel. And then I put together all my results, assuming that there's no order by. And that gives me the answer. Finding everything where, salary greater than 10,000, I have, let's say, a partition by name. I can go to my 1,000 partitions and get together everybody whose salary is greater than 10K and put my result together, and that's great. So I've gotten the entire result. Okay, but as we've talked about, there's this notion of partition pruning. And with range partition, I can get rid of some of the partitions. If I'm looking for names that are between K and P, I only have to look at the sites that are storing names between K and P if I have a predicate on name. Worst come to worst, I can always do my query by looking at all the partitions. My data is partitioned. By the way, there may or may not be indexes. I want to go back to this slide. I want to emphasize, we haven't talked about whether or not there's an index here. There might be, we're going to talk about indexes soon. But this is about where the data ends up being located. If I'm looking for something that's starting with F, I only have to look over here, even if there was no index. And if I'm looking for data with values between L and P, I only have to look over here and over here. I haven't told you whether there are any indexes existing. Maybe there are. Maybe there aren't. Anyway, with pruning, I only have to look at the places that are relevant. With hashing, well, again, remember, hashing is great for exact values. It's not so great for ranges. So, everything has to be accessed for a round robin. So I've gone over a couple of examples of how partition pruning works. There can be indexes. I told you indexes were coming. Here they are. Indexes can exist on each partition. And that can be useful for locality. Because what you do is you have an index on the data in each partition. So I can find a particular value. For example, if there's a situation in which I'm looking up where, and we'll see more slides on this, but if I'm looking at Finkelstein, if I have an index over here, I can find people whose name begins with Finkelstein, right? On the other hand, by the way, if I'm looking up for everybody whose salary is greater than 10K, I can have an index on salary at each one of these sites. So if I'm looking up everybody whose salary is greater than 10K, I am going to have to go to every single partition. But by having an index on salary that's local to each one of the sites, in parallel, I can look up everybody whose salary is greater than 10K. Okay, question? Should be fairly straightforward. It gets a little more interesting soon. What about when you have a unique index? So suppose that I, again, have the example that I have over here based on name, but I also have a notion of a student number, a cruise ID, or employee number. An employee number has to be unique. It's not unique at one of the sites, it's unique across all the sites, which means that if I'm inserting a new employee or updating an employee's ID, I have to make sure that everything is cool across all the different sites. Well, there are a couple of different ways that I could try handling that. Each of them has advantages and disadvantages. So you may be able to partition based on the thing that's your primary keyword that has to be unique. If you're doing that, then life is easy. If I actually partition the data based on the student ID value, then it's easy. I just have an index on each site, and I can make sure that no more than one person gets student ID 1, 2, 3, 4, 5. So that's pretty simple. But if I don't partition based on this unique / primary key column, how do I guarantee uniqueness? If I'm splitting up into 1,000 different pieces or even 10 different pieces, how do I go about doing it? Well, so if you have a primary index and you partition based on the primary index, everything is easy. But secondary indexes become, to say indexes on secondary attributes that aren't the way that you partition, it becomes difficult to deal with. So assume that you have the data partitioned by a base table key, like name in the example that I've shown you, and you have the situation where, again, the student ID is supposed to be unique, okay? So, if you partition based on the key, then you can insert locally based on the name, which is how we partition based on name. And everything is easy unless you have some other thing like the student ID, which is unique. That makes things hard, okay? We'll talk about uniqueness again in a second, also on this slide. But what do you have to do when you do a lookup that corresponds to a student ID? You have to go to all the different partitions. What do you have to do when you do a lookup based on salary greater than 10,000? You have to go to all the partitions, right? Because basically having the data partitioned by name doesn't help you do partition pruning. In the case in which you're trying to look up based on salary range, you have to go to every single place. Or if you're trying to do a lookup based on the student ID, you have to go to all these different places. So you have to go ahead and go to all the partitions. So, here's the basic idea. So basically what you need to be able to do is to go to every different partition to be able to find the values that corresponds to what's going on if you're looking up based on something which is different than the way things are partitioned. Okay? You can choose to do the partitioning based on something which isn't the primary key. And so you can have a search key which corresponds to some secondary key. The nice thing is that if you're doing that, then you end up having the nice advantage that you have to just take the data and the index and everything ends up being, relatively easy. So what you do is you have your index based on this other key, might be address or something like that. You know which node you need to be able to go to because you know how the data is partitioned by this secondary key, and then you actually get the data there. So it's basically going to be a lookup to be able to figure out where the data ends up being located and then get the data that corresponds to it, and that allows you to be able to get to the right place. And so that's how you do the insert, that's how you do the lookup. Everything is easy. And again, if you end up having something where you partition by the key range, again, that ends up being easy to be able to deal with uniqueness because it's just one place to go. So basically, here is the story that you have two choices. You can go ahead and index by your secondary key or not. And again, let me just run through this. You can either have one global index based on the secondary key. You look up in that index to be able to figure out where the data is located. Or you have the secondary index at every single node. So let me go over that again. In some ways the description on the slide isn't as good as it could be. Approach number one. I have an index based on a single index based on my secondary key, like salary. One index, which points to, find some values at this partition, values at that partition, all the rest of it. So I just have something based on salary. I have a B tree that I store, and I just have one index, and I look up for all the people whose salary is greater than 10,000. Here's another way of doing it. At every single one of my sites, I have an index of the people who make more than 10,000. What are the advantages and disadvantages? If I'm looking for everybody who makes 10,000, it's easy for me to look in the index. If there's just one index that crosses every different site, and I can look up and I can find, basically I can find where the people who make $10,000 are located. and then I just go to the individual sites for them and I get the data. So it was easy to do the lookup, and in particular, it's easy to, when I have something that's supposed to be unique, if student ID is supposed to be unique, if I have a single index for each value, then I can use the index to see, is that value already existing? Because I have one index based on it. Or what I can do is, I can have my index for every single one of the sites. So for example, if I'm looking at the people whose salary is greater than 10,000, I have an index at each of my 100 different sites. And I look up the people whose salary is greater than 10,000. And I put that together and I get everybody whose salary is greater than 10,000. But what if I was looking for something like cruise ID, which is supposed to be unique? Before I can do the insert, I have to check, is there any site that has cruise ID 1, 2, 3, 4, 5? And if there is, I can't insert the 1, 2, 3, 4, 5. I have to check everywhere for doing it. Whereas if I just had one index for cruise ID, then I could just check in the index and see if anybody has 1, 2, 3, 4, 5. And there are other variations of names that exist. As an example, what Teradata did was it partitioned the non-unique indexes by the base table key, okay? And so there would be things that end up existing at every single one of the sites that corresponded to the secondary index. So that's like the salary example I gave, where every site has the people whose salary is greater than 10,000. And an example where something needs to be unique, like the cruise ID, then it would see what you can do about partitioning the unique indexes by the secondary key. Meaning that there would be a partition of the index on my secondary key, where that index would end up being partitioned across k different sites, where I could end up looking it up. Not according to necessarily the way that the primary key ended up having the data separated. Question?
So we're a little confused about how the unique indexes are partitioned by the secondary key. Are you just saying that, so for each unique index, there's a secondary key that we're splitting the unique indexes up?
And the index itself is partitioned, yes. The index itself is partitioned, which may have absolutely nothing to do with the way I partition the base table. It just allows me to look up in the index in parallel, and I only have to look at the one place that corresponds to that value if I want to see that 1, 2, 3, 4, 5 is set up. So I would have the cruise IDs, let's say, in 12 different places. And if 1, 2, 3, 4, 5 is, if it exists, it's going to be in place number 3, which I can figure out based, let's say, on a hash to figure out where it should be. I can look at the thing that corresponds to 1, 2, 3, 4, 5 and see whether it's there.
We don't partition on the unique index because there could be a whole range of what's in.
No, what I'm saying is that is something that often gets done with respect to the unique indexes, and that's in fact something that Teradata exactly did. It didn't want to broadcast to all the different places. It wants to do the partition pruning, so it only has to go to the one right place for the index. By looking at the one right place in the index, it tells us the one right place for the data if the data exists. It tells us, does the data exist? Yes, there is somebody with 1, 2, 3, 4, 5. No, there isn't somebody with 1, 2, 3, 4, 5. If there is somebody with 1, 2, 3, 4, 5, I can then find it because the index will tell me where it's located. And if I'm trying to do an insert of the 1, 2, 3, 4, 5, knowing that somebody exists, it'll stop me. So the partitioning of the index can be very separate from the partitioning of the data. It allows me to do index lookup in a partitioned manner, in a parallel partitioned manner. But the partitioning of the index may be very, very different from the partitioning of the data. Because the data is partitioned based on name, not based on cruise ID. Okay? That's the important thing. The partition is different for the